we go. Hey, welcome back, everybody. We are going to continue on. We're going to do about 3 slides at the end of the chapter 15. It's a new reaction. We're not going to be tested over it, okay? But I want to introduce the topic because it's a little different than what we've done up to now. We will be testing on everything up to what I covered yesterday, and also the group activity, which we'll do in the second half of this, is directly related to what will be tested over. So that's what I want to make sure we understand. So, and then because I only have 3 or 4 slides talking about this new kind of reaction with benzene, we'll have plenty of time to do a review of chapter 14 and 15. I have 3 high notes for each of those chapters I want to make sure we hit during that review session. And then we can just do answers and questions and you know, any questions you have, we can cover. Okay, first thing we're going to do is administration. Of course, we have Zoom class today, yay. And we have our group activity this afternoon. You should have received an email with a PDF on that. Like before, I'll give you instructions when we get to that. If you cannot participate for some reason, go ahead and fill it out yourself and upload it to Dropbox, okay? As long as it's uploaded to Dropbox by noon tomorrow, we should be good. Okay, and you'll get full credit for it. The whole concept of doing it as a group is to get a different person's perspective. Hey, I look at it this way and it works for me. So that's why I prefer the group, but if you can't do the group, that's fine. Okay, homework is also due at midnight tonight. As soon as midnight happens, you can review it. Go back, figure out which questions you got right and wrong, and use that as part of your review for the exam, okay? Our exam starts at noon tomorrow and it'll go till 1:40 unless you have an ODS accommodation. And go ahead and log into that. You should have exam 2A or B. You'll be assigned it automatically when you come in. So just go ahead and do everything like you did before. I will be sending out an email tomorrow morning reminding you about restarting your computer and taking all your memory hog programs out and all that kind of stuff. So don't worry about that. That'll go out about 9 a.m. tomorrow morning. Again, next week on Monday, look for a new Zoom link for our next week's class. And next week, we're going to start with chapter 16 and 17. So that's aldehydes and ketones and carboxylic acids. So we're going to go and we're going to do those starting next week. Okay. So that is all the administration I have right now. Does anybody have any questions about what I've said so far? Looks like we have about 37 participants, so put it in the Zoom chat or put it on the, or just unmute and ask the question. Okay. Well, you guys are figuring out whether you want to do that or not. Let me go ahead and pull up my file for today's talk. I have plus, there we go. All right. Okay, getting to the end of the chapter here, so I can talk to you a little bit about a new concept related to what we're doing, what I'll talk about today. So, okay, I am going to go ahead and share my screen, so hopefully we won't glitch out. It's wrong. Let me see, my iPad might have decided to connect to something else. No, that's where it's connected. There we are. All right, everybody should be able to see some slides now. Okay. All right, so let me go ahead and move all the people over here. There we go. Okay, so up to now, we've done one mechanism for every single reaction we had in our aromatic substitution reaction. And it's an electrophilic aromatic substitution reaction, meaning we had to have the positive charge on something outside the benzene ring. The benzene electrons, because they're so much electron rich, they reach out and grab that positive charge and pull it in and then eliminate a positive hydrogen to re-aromatize. And that driving force is always to re-aromatize because it's so much more stable to be an aromatic compound than to be isolated double bonds. Okay, so the other mechanism we have available to us is called nucleophilic aromatic substitution, meaning that we can actually have attack by our nucleophiles. Remember when we were talking about alkyl halides, when we first started talking about mechanisms, we did an SN1 or an SN2 reaction. So that's a unimolecular nucleophilic attack or a bimolecular nucleophilic attack, okay? So now those only worked because of things that were sp3 hybridized. We would go in and displace something, or we would have a leaving group leave, creating an sp3 hybridized carbocation, okay? So in the aromatic system, if we try to do that, for example, we have this aryl halide here, this we have this benzene with a chlorine on it right here. You know, you're thinking, oh, hydroxide, if that was an alkyl halide, I could displace that chlorine and make an alcohol out of it, okay? But because of the stability of the aromatic system, we cannot do this substitution, okay? So a straight SN1 reaction does not work. However, we did find out that because of that partially positive charge on the deactivators, that the electrophilic substitution reaction is decreased as we add those electron withdrawing groups on there, or things with partially positive charge. Okay, but so we can actually now take that to our advantage. If it's actually taking electron density away from that ring, what if we instead used nucleophilic attack since it's less electron dense? Okay, so that's what we're going to talk about. This is the opposite mechanism for doing substitution reactions on the benzene ring. Okay, so in the nucleophilic aromatic substitution, the more electron withdrawing groups you have, the faster the reaction goes, okay? And it goes faster because we're again looking at it in the opposite direction. In the electrophilic attack up to now, we needed all that electron density. The more electron density, the better, and it can reach out and grab those positive charges here. Okay, now in this case, we actually have a negative charge coming in to attack the ring to do that substitution reaction. So just by adding, so in the previous slide, we showed you that just chlorobenzene itself does not react with hydroxide, even at high temperatures. You can't, it just doesn't work, right? By adding a single nitro group, we can actually do it at about 130 degrees, whole bunch of sodium hydroxide, and it will displace that chloride. It'll do that substitution reaction, okay? So we have hydroxide as an anion coming in and chloride as a anion leaving, okay? And chloride leaves because it's the weaker base, okay? Now, if one electron withdrawing group made that reaction possible, what happens when we add a second one? The second electron withdrawing group makes it easier to do it again because we're decreasing that electron density, and we can drop the temperature a little bit more, and our yields actually go up a little bit higher. But we're doing the exact same reaction. We're displacing that chloride, we're taking that hydroxide, a very good base, and displacing the chloride, which is a weaker base, okay? So, and by the time we add 3 nitro groups to our system here, we can practically do this at room temperature. Okay, it just spontaneously converts over in the presence of a hydroxide and generates our substituted material. And this material actually is well known in the explosives community as picric acid. So just an aside, you don't need to know that, it's just fun. Okay, so why does this work, okay? Okay, why does this only work with electron withdrawing groups? Okay. Remember when we did our first reaction, we actually were forming a cation that was moving around the ring, and that cation was stabilized by the fact that it can move around to multiple places. And in the case of having a lone pair on a substituent of the ring, that lone pair can donate back in and have a fourth resonance stabilized charge species, okay? That's why the electron donators with electron pairs added that extra resonance stabilized material, and it, wow, I can't believe I'm getting this many emails. Anyway, uh, okay, so in the nucleophilic attack, we do the same thing, except we are generating an anion, okay? We're having attack by the hydroxide, we're breaking aromaticity, we're generating an anion. But unlike the case where we had the positive charge moving around and being repelled by a positive charge, the positive charge actually helps us because we can stabilize our negative charge by having it adjacent to our positively charged electron withdrawing species, okay? So this intermediate here, this is enhanced if the electron withdrawing group is ortho or para to the substitution site, okay? Okay, just like, but it does not enhance substitution at the meta site. It only enhances ortho and para because, again, you want that anion to move around the ring and be next to that electron withdrawing group. So if the electron withdrawing group was in this position or this position, either of those ortho positions, it would stabilize that charge, okay? So this is why we have a slightly different mechanism and why electron withdrawing groups work for this substitution. So if you have something that you've already substituted and you have electron withdrawing groups, we have an opportunity to displace that and make other things like phenols and amines directly if we have electron withdrawing groups, because we're changing the mechanism. We're going from an electrophilic mechanism where we need a positive charge to a nucleophilic mechanism where we need a negative charge. And in the case of the nucleophilics, the opposite works. The more electron withdrawing groups you have, the faster the reaction goes. Okay. So that should be my last slide there. Okay. So I just wanted to introduce the topic to you that we can do nucleophilic substitution on there. And just like with the electrophilic substitution, you know, the opposite charge speeds up the reaction. So in this case, electron withdrawing groups make it faster. Electron donating groups make it slower or not work at all. Okay, so that's the last topic I want to introduce to you in chapter 15. Okay, there is another mechanism in the book called a benzyne mechanism, and I would normally go over that, but I think that we've learned a lot, and if we can do these multi-step synthesis where we're choosing which groups to put on first, I think we've really understood what I was hoping we would in chapter 15. Okay, so what I'm going to do now is I'm going to open it up for questions. If you do not have questions, I'm going to go back to my chapter 14 slides, and I want to hit on 3 topics. Okay, go ahead and either put your question in the Zoom chat or go ahead and unmute and ask it while I switch over to the other chapter. Okay.
I did have a question. If it's okay, I'd like to annotate on your screen to show like the example I'm really like looking for. A lot of times during like our discussions on aromaticity and stuff like that, we had say like a benzene ring. Forgive my crude drawing here, but a lot of times, like if we had like a say like an oxygen here, right, instead of that being a carbon, and there was like a lone pair located inside the ring, right? I'd like for you to clarify, if you could, please. I remember you saying sometimes like the lone pair counts towards aromaticity and sometimes the lone pair doesn't count. Could you elucidate further on that?
Okay, that actually is one of the things I wanted to talk about. So
beautiful, wonderful.
Okay, for these slides on tracks and on Canvas, there are 2 sets of slides on there. There's one folder that says full slides and one says video slides. Video slides are the ones that are blank that you can follow along. The full slides actually have everything written down correctly. Okay, so that was a question in the chat. So they should be both on tracks and on Canvas in folders labeled that way. And there's another question here in the chat about don't worry about nucleophilic substitution on the test. Yes, do not worry about nucleophilic substitution. I just wanted you to demonstrate that benzene is very flexible in how it can work. we want to focus on this electrophilic substitution reaction, and that will be what you'll be tested on, okay? So let's go over the three things I wanted to talk about in chapter 14 is go ahead and remember the nomenclature. We have those special names for those things, like with a methyl group on it's toluene, with a methoxy group it's anisole, with an OH group it's phenol. Those common names will be necessary to name the compounds directly, okay? So that's the first thing I want to remind you of in a review about chapter 14. The second thing I want to go over is aromaticity and finding the electrons that contribute to the aromaticity so that we know we have the right number of electrons, the right number of pairs of electrons, okay? So the first thing I want to remind you is the idea that we have the difference between aromatic and anti-aromatic, okay? Aromatic has 4n+2 electrons, okay? So if n is 1, if n is 0, that gives us 2 electrons. So we have 1 electron pair. If n is 1, we have 6 electrons. That's 3 electron pairs. If n is 2, we have 10 electrons. That's 5 electron pairs, okay? So either look at it as remember the numbers 2, 6, and 10, or 14, or remember it has to be an odd number of pairs. They both say the same thing. Just make sure that you are consistent in that, okay? So 2, 6, 10 is aromatic. 1 pair, 3 pairs, 5 pairs is aromatic, okay? In contrast, anti-aromatic meets all the other rules of cyclic, p orbital, and planar, but it has an even number of electron pairs. And so our calculation is 4n. So n starts at 1 with 4 electrons, that's 2 pairs. And then we can go to 2, which would be 8, which is 4 pairs, okay? So that's the difference between aromatic and anti-aromatic, okay? Now, if it breaks any of those rules, the pairs of electrons or the planarity or not having a p orbital available, then it is non-aromatic, okay? So that's those are the rules, and that's how to identify each of them, okay? Now, going to what the question was asked about which electrons to look for, that's another thing I wanted to draw your attention to, okay? So let's go and look at this particular one here to start with. The first thing is not only do we have to have the right number of electrons, we have to have the right number of electrons in the right orbital, right? Correct. So in the case of cyclopentadiene, because we have an sp3 hybridized carbon here, it is non-aromatic, okay? Because it breaks the rule of having a p orbital available to it. If you remove that hydrogen as a positive charge and leave the electrons behind, you have changed the hybridization of that carbon from sp3 hybridized to sp2 hybridized, leaving you a p orbital available to it, and you left those 2 electrons in that p orbital, okay? Remember, all the other sp orbitals that were already hybridized already have their electrons in them. So when you pull that hydrogen off and leave those 2 electrons from that sigma bond, both of those are going to end up in your p orbital, okay? So now you have a p orbital, and now you have to count the electrons. And in this case, we have 2 in the p orbital that was sp3 hybridized, and then 1 in each of the p orbitals that had the double bonds in them, for a total of 6, okay? So we have met all of our requirements. Therefore, even though we have a 5-membered ring, and we have a, you would think, okay, if we only had 1 electron in each of those orbitals, we'd only have 5 electrons. But we have 2 electrons in one of them, which gives us our total of 6 electrons, 3 pairs, therefore it is aromatic. So we can have aromatic compounds that are cations, we can have aromatic compounds that are anions, and we can have aromatic compounds that are neutral, okay? But so just because it has a charge doesn't mean it's not aromatic. We have to look for the total number of electrons available to us, okay? So that brings to the next question is that, okay, sometimes we see lone pairs, and sometimes those lone pairs are in the p orbital, and sometimes they're in the hybridized sp2 orbital. That's the next thing we need to look for. 2 electrons is 1 electron pairs, yes. So 2, 6, and 8 is aromatic. Those are electrons. Okay, 2 electrons, 6 electrons, and 10 electrons would be aromatic. 4 electrons, 8 electrons, and 12 electrons would be anti-aromatic. Okay, so do number of electrons or electron pairs, one or the other. It makes it clearer to do one or the other. All right, that's all the questions, good. All right, oops. Okay, so now let's look at which ones do count and which ones don't count. Okay, and when we look at these two, for example, we need to figure out which electrons we do count and which electrons we don't count. And we have to do that by looking at and assigning a hybridization to each of the atoms. Now, in benzene, because it's all these bonds, all the carbon hydrogen bonds and carbon carbon bonds are 120 degrees, right? If we had a hydrogen here, we know that those are sp2 hybridized trigonal planar, and that leaves that last p up and down, above and below the plane. Okay, so just like a carbocation, it's sp2 hybridized. Okay, so now we have to look at the nitrogen here. Okay, now when we think about nitrogen, it's like, oh, is it really hybridized that way or what? Okay, let's look back to what ammonia looks like. Okay, ammonia is pyramidal, right? Because the nitrogen is sp3 hybridized, it has a total of 5 valence electrons. So it bonds once to hydrogen to gain an electron, once to hydrogen to gain an electron, once to hydrogen to gain an electron. Now it has 8 electrons. Those last 2 electrons are in that other sp3 hybridized orbital. So electronically, it's tetrahedral shaped, but physically, it's a trigonal pyramidal. Okay, so that means that nitrogen can be sp2, sp3 hybridized. Okay, in the case of pyridine here, the part of because it's has a 120 degree angle here in the middle here, we're going to say it's also sp2 hybridized. Okay, now if it's sp2 hybridized, it has to have a p orbital in it, right? Because the other 3 orbitals are going to be that trigonal planar. And so there has to be another orbital there. And in the case of pyridine here, we like to say that the orbital, because there's a double bond between the nitrogen and the carbon there, that double bond is always a pi bond, right? Pi bonds are only made from p orbitals. So because there's a double bond to nitrogen here, we know there's a p orbital there, okay? And the electrons making that double bond are in the p orbital, okay? So if that's true, that makes these electron pair here in the sp2 hybridized orbital, okay? So if you see a double bond to a nitrogen, one of those electrons, that double bond, the nitrogen has one of those electrons in that pi bond, okay? And that's where the p orbital is, okay? Now, in contrast, let's look at our next structure here. This is also flat and planar. And notice this is 120 degrees and 120 degrees and 120 degrees, okay? That means all 3 of those sigma bonds are the sp2 hybridized orbitals, meaning that the last 2 electrons has to be in the only remaining orbital. The only remaining orbital we have is that unhybridized p, making both of those electrons in our p orbital, and they count toward aromaticity. Okay, so we have 2 in this p orbital, and then 1 in each of the other p orbitals, giving us a total of 6 electrons, or 3 electron pairs. Does that answer your question?
Sort of. Sort of. I'm still trying to kind of synthesize the information.
Okay.
Um, drawing like so if like one of my takeaways is that if this guy, this lone pair here, if this is located outside of the ring, does that mean that it doesn't count towards aromaticity? Would that be a good rule of thumb? Or
Um, well, where you draw that lone pair, it could be drawn inside or outside. It just happens to be drawn inside and outside on this particular slide.
okay.
Okay, so for example, I think I show some other heterocycles here. Huh, interesting. I don't think that's a great way to say it, although it does seem to follow the order on this, because
Okay.
you know, I, I don't think that's universal, but it's true because the one outside isn't, but the one inside is. The one outside isn't.
Dr. Irvin,
Yes.
does it have to do with nitrogen itself? Because nitrogen likes to have like 3 bonds, and so since, well, it likes to be bonded to 3 things, right? And so like since it's only bonded to 2 things, that third electron pair is like, that's for nitrogen itself.
Well,
And then when it's bonded to hydrogen, then the extra electron pair can go into the vertical like pi orbital.
well, technically, this nitrogen here is bonded to 3 things. It's bonded that carbon twice. Once in a sigma bond and once in a pi bond. So this nitrogen is bonded 3 times, twice to one carbon and once to another carbon. So the way I like to describe it is that in the case of this double bond, you know that double bond has to be a pi orbital, right? It's a pi bond. Pi bonds are only made with p orbitals. So the electrons in this double bond have to be in a p orbital. Here, we don't have a double bond to nitrogen, okay? So those electrons have to be in the p orbital, okay? So in the case of this, if this was sp2 hybridized, one of the bonds is sp2 hybridized, the other bond is sp2 hybridized, one of the lone pairs is sp2 hybridized, leaving the last lone pair in a p orbital. Okay, so in the reason nitrogen bonds 3 times is the fact that it had 5 valence electrons. Okay, so it already had 5 valence electrons. It only needs 3 more to make its octet. That's why nitrogen typically bonds 3 times. Oxygen has 6 valence electrons, and therefore it only needs to bond twice to fill its octet. Sulfur has between 8 and 10 valence electrons because it's bigger and it has another shell. So we typically see it bond 2 times or up to 4 times to make its full shell. So, well, your rule of inside the ring versus outside the ring seems to follow it the way these are drawn. I can't say that's a universal rule.
Yes, sir. Okay.
Okay.
So just be mindful of like, you know, which electrons are hybridized and which ones must contribute to like or be assigned to the
Right.
sp2.
Right. Because think about it, every sigma bond has to be a hybridized bond. Okay. It has to be an sp, sp2, or sp3. Okay. All pi bonds have to have at least 1 p orbital. Okay. So if you see a double bond to nitrogen, then that means the lone pair is in the p or the lone pair is in the hybridized orbital. If you don't see a double bond on nitrogen, that means the lone pair is in the p orbital. Okay, and in the case of the sulfur and the oxygen, 1 pair is in the hybridized orbital, 1 pair is not in the hybridized orbital.
Okay, thank you very much, sir.
So let's do one more. Let me do one more thing. Let's look at this one right here, pyrimidine right here. Okay, the lone pairs on each of those nitrogens are in the hybridized orbital because there's a double bond to each of the nitrogens. So that means those lone pairs are in the hybridized orbital and don't count toward aromaticity.
Can you repeat if you don't see it in the p orbital, it is, and then if you do?
Repeat the question.
Can you repeat what you just said about if the lone pair was in the p orbital and if it wasn't?
Okay, so in the case of nitrogen, if you have a double bond to nitrogen, that double bond is involved. That double bond uses nitrogen's p orbital, and that makes the lone pair in the hybridized sp2. If the nitrogen doesn't have a double bond to it in a ring, that means that the lone pair is in the p orbital. So in the case of pyrimidine, because each of these nitrogen has a double bond to it, that means the lone pairs must be in the hybridized orbital and are not part of the aromatic electron count. But if we look at this one right here, only one of the nitrogens has a double bond to it, okay? Which means these electrons are in the hybridized orbital and these electrons are in the p orbital and count toward aromaticity.
So just like to make sure, just to take away, like, because I'm really frightened about this topic. I want to make sure I get it hammered home. If a lone pair is in the hybridized orbital, it does not count towards aromaticity. But if it is in the p orbital, that's when it counts towards aromaticity.
Correct.
Gotcha. Thank you so much.
P orbitals count toward aromaticity.
How can we know if it's in the s orbital or the p orbital?
Okay. Whenever we have to think back to hybridization. Okay. sp3 hybridized means all three p orbitals are hybridized, and therefore we don't have a regular p. Okay. If it's trigonal planar, right, that means it's sp2 hybridized. Means two of those p orbitals have been hybridized and will form a total of 3 bonds, and that leaves the other p empty, or leaves the other p unhybridized. And that unhybridized p orbital can be used to help figure out. In fact, you must have an unhybridized p orbital to have something be aromatic.
So the nitrogen in pyridine, I feel like it's sp hybrid. Wait, yeah, because it's bonded to two things. Like there, like 2 electron domains are used up.
2 electron domains are used up to make sigma bonds, but the third hybridized electron domain has the lone pair in it. So the lone pair is actually in the third sp2 hybridized. The first sigma bond is the first sp2 hybridized. The second sigma bond is the second sp2 hybridized. The lone pair is in that third sp2 hybridized, okay? And then the p, the unhybridized p, is used to make the double bond. Sigma bonds are always hybridized. Pi bonds are always p's.
Okay.
In aromaticity, we always count p's, unhybridized p's.
So even though it's trigonal planar, that electron pair is not going to be in a p orbital.
Correct. And that is demonstrated if we look here. Okay. See, if we look here, I'm going to do it in, let's see, red right here. See, these 2 electrons are sticking out. They're in the trigonal planar configuration. So these 2 electrons are in their sp2 hybridized orbital. But in the case of pyrrole, these 2 electrons are in the p orbital, and the hydrogen that it's bonded to is in that sp2 hybridized orbital.
Okay, so in pyridine, it's still an aromatic molecule because that p orbital is available for delocalization.
This p orbital is available for delocalization, and it has 1 electron in it. Yes.
Okay. Okay, yeah, that makes sense because it adds up to 5, right? Because it's got 2 on the outside and then 1 in the p orbital, and then 2 are bonded.
Yes.
Okay.
I have a question about periodic table in Top Hat. We only have to remember 4 valence electrons, 5 valence electrons, 6 valence electrons, and the in order of electronegativity. So I typically don't include a periodic table because we only have to remember those 3 things. So does that answer your question? Okay, so, all right. So we had 3 things in chapter 14. Naming things, the 4 rules for aromaticity and anti-aromaticity. You break any of those and you are non-aromatic. And where to find your electrons in heterocycles. Those are the big 3 things in chapter 14, okay? So I'm gonna switch over to chapter 15 and look at the big 3 things in chapter 15. Okay, so again, go ahead and type your questions in Zoom chat. I think I've answered all the questions. Okay. Okay, let's see. So the big thing about the first part of chapter 15 is that it's the exact same mechanism for every single reaction, okay? So that makes it really nice in the fact that it's the same mechanism no matter what we do, okay? So, and again, we're not being tested over the nucleophilic, we're only being tested over the electrophilic here, so. And the same 3 steps happen in every single one of these reactions. We generate our electrophile. Usually we take our reagent plus a Lewis acid catalyst to generate that positive charge. Occasionally we add like sulfuric acid to nitric acid and generate the nitronium ion, okay? But in all cases, we're generating that positive charge. In the Friedel-Crafts reactions, we're generating carbocations, okay? So that generation of the cation is the first step, okay? Now, the second step is attack by the benzene ring to reach out and grab that positively charged thing. And that's always the slow step. We have to wait around for the benzene to say, oh, okay, I'm close enough. Yeah, okay, I can do this. And then the next step, the losing of that positively charged proton, is always our last step, and it's typically a fast step because it wants to re-aromatize, okay? So the mechanism is the first thing I want to draw attention to. Okay, questions about the mechanism? Okay, then let's go then. The second thing we want to talk about is that, you know, it's really, really, you know, one mechanism for all the different functional groups. I think that's a really cool thing. And the fact we just have to remember to generate our positively charged species correctly, okay? The second thing I want to draw our attention to is that series of electron withdrawers and electron donators and how they affect our reactivity, okay? And that is summarized on this slide here. There we go, this one right here, okay? And I wanted to make sure, all right, sorry if somebody's getting nauseous from this, I don't know. Okay. This slide right here is the next most important thing. Directors and activators. Most of the time, they're the same thing, except for the case of the halides, okay? They're ortho-para directors, but slightly deactivating. Okay. But everything else here, all of these ortho-para directors are activators. And it has everything to do with the inductive or resonance effect that gives more electron density to the benzene ring. The more electron density it has, the more likely it is to reach out and grab that positive charge. Okay. So the meta directors are all electron drawers, and they are all deactivators. And they're all deactivators because either inductively or by resonance, they pull electron density out of the ring, hence electron withdrawing groups. Okay. So knowing these two, this compare and contrast between the meta directors and the ortho-para directors is number 2 most important thing about chapter 15. Okay. And we did go over why the different effects have different things and how they affect our activation energies. And that's come on. Go, move, there we go. Okay, and we went through why those activations work because of the stability of either having 3 or more resonance stabilized intermediates. Okay. And the last thing about this chapter that is really important is the fact that the Friedel-Crafts reaction is very difficult to stop at a regular, just a single alkylation, okay? So we have to trick it, okay? First of all, the Friedel-Crafts alkylation forms a carbocation. That carbocation is, if it can rearrange, it will, okay? If it does rearrange, that means we really can't get these straight chains hanging off a benzene ring without doing something special. And we have 2 workarounds for that. The first workaround is to do a Friedel-Crafts acylation and then reduce down that ketone, either using the Clemmensen reaction or the Wolff-Kishner reaction. One uses zinc and acid, or tin and acid. The other uses a hydrazine or a base. Either one, they both work. That's the only way to get long straight chain straight chains off of there. It's also the only way to get just one chain on there in high yields. Okay, if you had, if you were trying to do a Friedel-Crafts alkylation on benzene, you rarely get monosubstitution. You typically get a di or tri substitution. So to make it clean and make it have a single reaction, the way to do it is to do a workaround, do your Friedel-Crafts acylation first, because remember that aluminum chloride complexes with the carbonyl formed and stops additional reactions. So you only get one acylation ever in a Friedel-Crafts acylation. And then if you reduce down that carbonyl, you can actually do it again. Now, once you reduce it down, it's now an ortho-para director and an activator. So make sure we remember that, okay? So the last thing about the chapter is our order of addition, okay? Knowing the difference between our activators and our deactivators, and knowing that they direct one way versus the other, is important for us to decide which order of the reagents we're going to use, okay? And we're gonna do that in the activity I have planned. You'll see that, you know, doing it one way or another, you know, you get to strategize about how to do this direction versus that direction, okay? And so those are the 3 big things about chapter 15. All right, questions about chapter 15 now.
On the exam, will there be questions where we have to like combine different different reactions?
There will be a couple, at least multi-step synthesis, two steps, like to make this product, which reactants would you use in which order? Yes. So it'd be something like here, you know, a 2-step where we you know, add a, we do an acyl group here, and then we would nitrate and then deprotect, that kind of thing. Yes.
Okay.
And we'll get additional practice in the group.
Oh, we're going to practice that right now in the group?
Yes, we're going to practice that in the group.
Okay.
Okay. Other questions?
Just to kind of hammer home the mechanism of the electrophilic substitution. Right? You said the first step was generation of the cation. Second step was the electrophilic attack. And then the third step was when it lets go of the hydrogen and regenerates that pi bond?
Correct.
Cool.
So, and the generation of that positive charge is a little different in each of them, but it always involves an acid-base reaction to generate your positively charged species or partially positively charged species.
That's kind of when we get into like the generation of the complex, right? And that can get kind of tricky.
Correct.
Okay.
I mean, it's the same mechanism for you know, the Friedel Crafts always has attack by aluminum chloride. Aluminum chloride is your Lewis acid. Your substrate is acting as the Lewis base, but yes.
Okay. Okay.
That generation of that positive charge is always first. That attack by the benzene onto that positive charge is always second. And that elimination of hydrogen of the proton, the H plus, to re-aromatize is always the third step.
And that's also considered like the fast step, if you will. Gotcha. And then, okay, so for the Friedel crafts, you said single alkylation was hard. So first we have to do acylation, then we reduce down, and we just continue that process.
Correct.
Perfect. Thank you so much.
Okay. All right, we're coming up right on 12:48, so we have a few minutes left to talk and ask questions and stuff like that. And then what we'll do is we'll go ahead and stop recording and close out. I'll open the room back up, and then at 1 o'clock, be prepared to do the group activity. And I think I have one group I know I want to assign, and everybody else will be assigned randomly at that point.
How many questions are on the exam?
There are 30 questions again.
Okay, thank you.
So each question's worth 3.33333 points. It rounds up somewhere, I don't know. So in the final exam, we'll have 70 questions on it, but each of our weekly exams will have 30 questions. And it's pretty much evenly split over the chapters we're studying that week. It's only the chapters on that week and any foundational information you must have, like carbocation stability. Well, we learned it last semester. You kind of need to, that foundational information you need for this test, but not directly, just indirectly. Okay, well, I'm going to go ahead and stop recording and stop sharing here.